Have you ever wondered what keeps a DC generator from functioning below a certain speed? In the world of DC shunt generators, there exists a pivotal concept known as critical speed. It's a term that might sound complex, but it essentially refers to a specific operational threshold. Critical speed is defined as the speed at which the shunt field resistance of the generator matches the critical resistance. It is the speed below which the shunt generator just fails to build up its voltage without any external resistance in the field circuit. But what does that mean in practical terms? Imagine a scenario where a DC generator is running slower than this critical speed. At such speeds, the generator struggles, failing to build up sufficient voltage. This phenomenon occurs because the field resistance line does not intersect with the open circuit characteristic, or OCC, curve at speeds below the critical speed. Therefore, the generator cannot generate the necessary voltage to function properly. So, critical speed is not just a number, it's the threshold that ensures your generator produces power effectively. Before we dive into the mysteries of critical speed, if you haven't watched our previous video on critical field resistance and open circuit characteristics of a DC generator, I highly recommend checking it out. It will give you a solid foundation for understanding the concepts discussed here. The link is in the description and the I button above. How do we find out what the critical speed is for a specific DC generator? Let's dive into the fascinating process of determining the critical speed, which is essential for ensuring that a DC shunt generator functions efficiently and safely. The journey begins with the open circuit characteristic, or OCC curve. This curve is pivotal as it represents the relationship between the generated voltage and the speed of the generator under no-load conditions. The first step in our exploration is to draw this OCC curve at a given speed. Let's call it N. Now imagine this curve on a graph sweeping gracefully upwards. Next, we draw a tangent line OB to this curve. This tangent isn't just a line, it's a graphical representation of the shunt field resistance. Now here's where it gets really interesting. We need to determine the critical speed, denoted as NC. To do this, we draw another open circuit characteristic curve, this time at the critical speed we want to find. We then draw a line OP that is tangent to this new curve. The magic happens when we draw an ordinate, let's call it line AB, intersecting our tangent OP at point C. The ratio of the intercepts on this ordinate, specifically AC divided by AB, provides us with a crucial ratio of NC to N. And if we multiply this ratio by the initial speed N, and voila, you have the critical speed NC. By following these steps, you can determine the critical speed to ensure your generator operates within safe and effective parameters. If you found this explanation helpful, please like, share, and subscribe for more insightful engineering content. Stay energized and keep generating knowledge.